はじめまして。私はエリックです。ドイツ人です。テクニカエンジニアリングの会社員です。日本語で学生です。よろしくお願いします。今日は英語で発表します。So, for the English speakers, I am Eric, and I will be presenting in English. Thank you for joining me today to the presentation about Automotive Ethernet testing, review of the past 10 plus years, developing strategies, concepts and solutions by Technica Engineering in this year's Nikkei BP event. I hope everybody is safe and healthy, and still wishing after this 2021 event that we might soon meet again in person. Let me talk to you today about the things that Technica Engineering has learned in the past 10 years when it comes to Automotive Ethernet testing. For this reason, for this purpose, I have the following 6 points. First, I will give you a very brief introduction about Technica Engineering and Automotive Ethernet. Then I will delve into the quality requirements of data transport systems. That's the main thing that we're talking about. I will then talk about the testing considerations, so what strategies and concepts we have learned in the past 10 years through the integration of Automotive Ethernet. What are the best practices in this case? I will remark on the importance of test tool reliability, because in the end, measuring your traffic, measuring your data in the car is super important. And I'll give you an overview of the best practice test solutions that I can share with you today in this Nikkei event. And obviously in Japan, we are present with our local distributors for products, the company Galogic, and our local engineering partners, the company Toyo Corporation, which in Japanese is Technica, Toyo Technica in fact. So you please keep in touch with the guys in real Japanese, not the basic one that I am still learning. So, who is Technica Engineering? Just really briefly, we are a young company founded in Munich, Germany, 13 years ago. Today we are more than 500 employees with a very consistent growth. We are present globally through, in part, our own offices in the United States, for example, in Barcelona, Spain, in Tunisia, in Sfax in Tunisia, and obviously our headquarters and our logistics center in Munich, Germany, and also throughout the world with our partners in the different regions. We have been working from the beginning on in R&D, working directly with automotive car makers in the introduction of new communication technologies in the car. Currently, we are evaluating 10 base T1S, 10 gigabit or multi-gigabit base T1, and we have been providing key developments for the technology in this segment. We were the first ones to provide a converter for 100 base T1, for 1000 base T1, as you can see on the bottom left of this slide. Also the first to provide logging solution for automotive back in 2011, the Media Gateway. And currently, we have launched products that are cutting-edge technology, the so-called capture modules for all the relevant communication systems inside the car. As a company, we have 63% of our revenue on engineering services, which is why it's important to have an engineering partner in Japan, and 37% of our revenue based on product business, which is why it's relevant to have a product distributor in Japan. Moreover, what Technica Engineering has to offer since 2008? Well, since the early introduction of Automotive Ethernet, and I will touch about this in a following slide, the focus there was how to reprogram the ECUs in the car in less than 15 minutes instead of in 16 or more hours. This was a successful project done at BMW where Technica was supporting with testing solutions. This first application was done back then by now our CTO Thomas Königseder. Back then he was at BMW, the responsible for introducing this technology. Technica has been working very, very closely in this region since then. Technica Engineering has provided several projects which are of maximum importance when it comes to architecture, system integration and testing, not only with BMW, obviously also with other OEMs and basically all the tier ones that have to do with Automotive Ethernet ECUs worldwide. And we have provided the technical supervision of strategic EE components such as switches, gateways, domain controllers. We provide A0 samples of these kind of devices for OEMs, PCB reviews and so on. As I said, since the beginning, we started working with Automotive Ethernet. Exactly how we did the key evaluation of the early stage integration of what was then broader reach. When this was successful, provided testing tools such as converters, logging systems. Then we helped in development of IOP, interoperability tests for this technology because it didn't exist. And we helped test houses understand how to work with it and how to bring it on the market. Once the silicon was available, we provided 1000 base T1 converters as well, and started working then in the new speed grades, which are now being introduced, multi-gig, 10 base T1S, and security aspects such as MACsec, IPsec, and so on. And started working with multiple OEMs also in Japan when it comes to some IP introduction, service-based communication, architecture validation, robust communication, and so on. So with Technica Engineering, you have a partner that has the deepest experience and longest experience in the industry when it comes to Automotive Ethernet. Where is Automotive Ethernet used? You have heard this many times, but I felt it would be incomplete if I don't mention it, at least really quickly. Essentially, we are using Automotive Ethernet in the infotainment, the ADAS, the telematics, and body functions. There's a strong switch towards domain architecture, as has been discussed in multiple previous presentations, due to the reduction of cabling and weight and improving of space constraints. Currently, most of the OEMs are using Automotive Ethernet in different approaches, so nobody is really doing a pure domain or a pure zonal or a pure centralized architecture. This is due to the way that every OEM has used has developed their own EE architectures. With the new speeds that are soon to come, we can all expect to have major changes in the architecture structure. Many new ways of architecture will be possible now. And one important thing to remark here in the history of Automotive Ethernet implementation is that every OEM pretty much uses every protocol in their own flavor, let's say. Yeah, every OEM ends up using UDP/NM, DoIP, some IP in slightly different ways. This is important to point out because when it comes to testing, which is what this talk is about, that is quite relevant. So let's go to the next topic, quality requirements of data transport systems. I think talking about Automotive Ethernet without remarking on one of the technically most important topics would be incomplete. You have heard this many times, but I would just want to point it out again. Why do we have Automotive Ethernet? It's because standard Ethernet, 100 base TX, fast Ethernet, cannot be used in cars because the EMC emissions are not compliant to the automotive requirements. You can see in this graph, this is a measurement from Technica Engineering. Maybe you have seen it in the Automotive Ethernet book from Dr. Matthäus and from Thomas Koenigseder, or maybe in other papers. This was done by us many years ago. The green line represents the maximum allowed emission level of the strip line measurement for EMC, and the red line represents the strip line measurement of the EMC emissions of fast Ethernet. And as you can see, between 20 megahertz, or actually above 10 megahertz, and all the way to round about 130, 120 megahertz, the emissions are above the allowed level, the emissions level. This causes disturbances in communication systems such as CAN and FlexRay, which makes this technology useless for automotive purposes. When it comes to the solution that now today is known, standardized 2015, but started working with this back in 2009, broader reach, of course, is within the limits. One of the requirements that's essential is EMC. Other quality requirements of data transfer systems are that now that we have a new physical layer, so essentially what we are changing is the medium, what we call the medium, so the the cable, the connectors, the MDI, the medium dependent interface, so the PHY itself, the chip that allows for communication between Ethernet, two point-to-point components, and that is essentially what is new now with Automotive Ethernet, whether it's 100 base T1 or 1000 base T1. This has many requirements. So first of all, you need to have proper cables and connectors, which some of them I am showing you here. And other requirements you can see in this list are quite a lot. Essentially, I don't want to go through all of them, but this is very important to point out when it comes to data communication systems, and many things can go wrong. That's why I'm showing the next slide. When it comes to things that can go wrong, the PCB might be wrongly designed or the wrong components might be used. In this case, we have an example of the measurement of 5 devices, which we have measured in terms of establishing the Ethernet link. This is an old measurement. We have shown it at the Open Alliance, at the SAE, and different places. And 4 of these 5 components have mistakes. You can see highlighted with the blue bars over here. 4 of those the devices have link establishments that have taken more than 100 milliseconds. On the x-axis, we have the logarithmic scale for milliseconds. And we have in red the aggregated number of measurements for the number of links that were established. We did millions of measurements here. Even with the red, the little red circles, you can see on the right side, 2 of those had multiple times where the link was not established at all. So essentially no communication. That obviously is unacceptable in the car. And only one of the components here has link establishment within plus minus 100 milliseconds, which is necessary. What we're trying to say here is hardware design and choice of components is super important. That has to do with the requirements for data transfer system. So now that we have touched on the history of Automotive Ethernet, what Technica has to do with it, and what requirements are there for data transfer systems, let's go to testing considerations, some strategies and concepts. First of all, there are 4 holistic steps that need to be considered when testing. And in the automotive industry, the V model for development is a very good benchmark. I will touch about this in a second. Then the OEMs need to have a proper test concept and test specifications for this technology. Some of them exist through the Open Alliance, but obviously for the EE architecture of every OEM, they need to be adjusted and adapted. Then for every step of testing, you need different implementations. So you need component level testing, you need system level testing, full network testing. When you finalize, this is more for the tier 1s, when they make the components, they need end-of-line testing, and obviously you need full vehicle testing. And each of these testing strategies have different requirements. And then what Technica recommends here is in order to ensure the reproducibility of test results, which is extremely important from the beginning till the end, is the choice of tools and the use of the same tools for the same test purpose. So let us talk about this for a second. On this slide, you have the V model simplified as everybody knows it. On the left side, we design our system from more abstract to more precise. On the bottom side, we develop and we integrate the different software components, also electronics and mechanical components. And on the right side of the V model, we talk about integration and testing. So on the bottom side, once your software integration takes place, there are continuous integration and different unit software-based tests that need to be done. These need to be repeated, so an automation system needs to be put in place. Then when the components are available, there are gray box tests, which are very important to be able to have a debugger and at least have some information of what the ECU is doing. You need to consider functional safety, AUTOSAR, functional requirements to be tested. So here you still need software in the loop, but you integrate things like hardware in the loop. Then when the components themselves are partially tested, of course, the tests continue throughout the whole life cycle. now you start to get different kind of hill systems where you test the system integration, where you're mostly looking at black box communication. So what happens between the ECUs. So you need different kinds of test systems here and different kind of test benches. Then you go to the system test, where you see the whole system, all the components are connected together. And here you have different requirements of the testing framework and the hardware and software. And finally, vehicle test, where your test systems need to cope with things like battery management, temperature, things like this. So that's, let's say, to follow the V model. On the point number 2 that I mentioned, for each of these steps you need an appropriate test concept, and obviously you need appropriate test specifications, which need to be adjusted to the EE architecture of every OEM. Now, on the implementation phase, when it comes to component test, it's important to consider the multitude of protocols. This is completely different to what the OEM is used to when it comes to LIN and CAN. Most of OEMs have already realized this. Here there's a very quick presentation of multiple products in Automotive Ethernet. In black, some of IT standard protocols that already exist. In pink, peach, other protocols that are more automotive specific. In things like GPTP, there's a specific, this is for time synchronization, a specific profile for automotive. Some of these test cases you want to test in a test house. For this, there are so-called Open Alliance TC8, the technical committee number 8, has specified some test cases for physical layer, for different kinds of protocols. You might need some specific tools for that. I'm showing some of partner companies over here. Then obviously you will need for the component tests in your different stages of testing, different kinds of hardware in the loop test benches, depending on the complexity of the ECU. And what's important to mention here, what Technica has realized, is those TC8 test cases and all of those hill tests that look at the functional part are not covering the non-functional aspects of the quality of the implementation of the protocols. For this, we have realized with multiple OEMs, we have successfully provided so-called Ethernet test suites. That's the name we put it. It's very generic. So these are specific tests to look at the proper implementation of the protocols on the ECUs upon every software release. This has to be tested. Very important to remark. And when it comes to integrating all of these ECUs, you need to do partial network tests, especially with those ECUs that have to do with Automotive Ethernet, because the communication nature is very different than CAN, LIN, FlexRay, SerDes, and others. So an example over here to be seen as a picture. Now, let's go to the next slide. In here, I want to present you just really quickly how the test suites can look like. This is just a very general, broad example. There may be different levels of test suites with different numbers of test cases. So you might want to have sanity, what we call sanity checks. So just a few number of tests to see whether the EC was properly flashed, whether it's communicating properly. Then you want to go to a little bit more deeper tests, the so-called pull test, where you have a couple dozen maybe, depending on the complexity. This takes obviously different amounts of time. You can feed back to the developers how things are going. Then we have other strategies like the nightly tests with a couple hundred test cases. And when this software proves to pass most of the tests, you can go over to weekly tests where you have thousands of test cases to execute. And then if the software and the hardware combination is proper, meaning there's not so many errors along the way, the developers don't have to provide too many bug fixes, then you can go to full validation or complete device validation, which will take up to tens of thousands of test cases. Just to give you a feeling on the test depth. Then on the different kinds of test benches, because I have mentioned this, you can see on this slide on the far right, you have really big hill systems that you need to to stimulate your ECU on all the available interfaces that it has. Some of them will be very simple, like just a camera with power and Ethernet, and that's it. Some of them will be very complex, like body and central gateways and so on, which will need bigger systems. So for this you need dedicated test cases, also test benches. When you do partial network testing, you need maybe something more sophisticated. You don't want to stimulate so much, you want to look at the traffic. So for this you need proper measurement devices that will be able to capture your data, give you timestamping information, give you reliability information on what's the quality of the cabling, the signals, counting packets and so on, counting if there are errors on the CAN, on the Ethernet and so on. And then you want to go to full network tests where you have all of the real components of the car connected together, and here you might want to put partially simulation of ECUs that are not present or that would normally be working differently in the car. And finally, you want to do full vehicle tests. Of course, I cannot show you pictures of this because it's all NDA protected, but you can imagine a whole car and you want to capture all of the traffic in there. So now that we have seen also the test benches, let us go to the last point again of the best practices of strategies in testing and concepts of testing. Very important point, use dedicated tools for dedicated use cases. What do we want to say with this? If you have a simple conversion, what you want to do is you want to go on a physical layer conversion, and you want the hardware to be properly developed. As I showed before, improper developed hardware can give you big problems, and you want to have no manipulation of data, no conversion to other types of transportation system, and you want to make sure that this is 100% reliable. When it comes to Ethernet and you have multi-directional communication, let's say you have 3 ECUs or more ECUs, they want to communicate with each other, maybe you even have interfaces for your PC, then you need what Ethernet generally uses for communicating beyond point-to-point, which is a switch. There's nothing better than having a silicon implemented switch that is properly tested, properly configured, properly implemented with full managed features such as double VLAN tagging, single VLAN tagging, filtering, forwarding, and so on. You might even want to have some ARL functions there so that you can execute exactly the communication steps on your test environment that you want. Think about, there are switches in your network, and if you use switches as a testing system, it's perfectly okay, but you need to know what you're doing, especially with double VLAN tagging. And finally, when you're doing tapping, so essentially test access point, you have to break up the lines here in Ethernet. This is something I did not mention specifically, but when we change the physical layer, also the need for breaking up the lines appears, because you have scrambled data, because you have PAM3, so voltages overlap, because you have a lot of data going through, so you cannot use a simple stub like with CAN-FD FlexRay. You need to actually break the Ethernet lines, and this needs to be done really in a very, very clean way. Technica has more than 10 years experience doing this, and you need to have a dedicated system that does this and that is properly tested for deterministic latency. So, summarizing, for the 4 steps to holistic testing, as I mentioned before, following the V model, every testing level requires different test racks, let's say, testing concepts. Hardware and software framework have to be adapted. A proper test concept must be developed in itself by the OEMs. This is responsibility of the OEMs. And the test specification, even those that exist, they are there, but it's not enough for the EE system of every OEM. On the implementation of the test benches, I have shown you some of the examples, but nevertheless, point number 4, you need reproducibility of test results. So for a specific use case, it's important to use a specific dedicated tool that will be reliable, that will be properly implemented, and will give you the results you need, and use for that use case throughout the whole V cycle, always the same tool. Now, going to the importance of the reliability, because I've mentioned reliability. What do I mean with reliability? On this slide, you can see a list of the different points that a reliable tool has to fulfill. It has to support the bandwidth, which means also uplinks need to support everything that is being captured. Link establishment, which is crucial. If you don't have a proper link establishment, the whole thing doesn't work on your measurement tool. This is extremely important. Deterministic latencies, especially in the taps, as I mentioned before. Otherwise, when your network has measurement devices, it will behave completely different than when it does not have the test devices. With our tools, we have found out this is necessary, this is important. Power range, when you're in a car, maybe you need 24 volt, but generally 0 to 12 volt. And when your battery goes down to 8 or 6 volts, it still has to work, very important. Full throughput of the data, which you have to test for 100 base T1, 1000 base T1, with big packets, small packets, and a mix of that. Diagnostics of status, what is going on with my tool. Startup time, does the tool start up before the ECUs? Wake up concept, do the tools go to sleep? Can I turn them on? Will it be fast? Ease of configuration, because we have seen many delays in projects because our configuration was not right. Can I check the configuration after the fact? Using existing standards, especially when you want to be compatible with multiple tool vendors like Ethernet, yeah, RJ45, everybody can use that, and use reliable equipment for the complete test tool chain, because we have seen the use of, let's say, loggers that were not really that good and they lost packets, and that's a big mistake not to have the right tools. All right, so with this list being said, what happens if not? Well, if you lose packets on your measurement system, you find mistakes that are not on your test system, they're on your measurement system. So the tools they cannot have something like packet loss. If you have logs of received data that is not synchronized, you don't know when the data came at what point, this is not acceptable. If you have incomplete data because the message throughput was not there, because there was a manipulation of the data, then this is unacceptable. When you execute your tests and your measurement system is not starting fast or is not performing the right way, your automation will fail, and this is also not acceptable. And the most important topic is, if your measurement system is not reliable, you will lose time. The whole testing will be inefficient. The whole project will take a lot longer, will cost a lot more money, and the results will be delayed, which is in the end bad for everybody. So, going to the last point, overview of the best practices of test solutions. Today I want to highlight this concept. So you can see in this animation we have 4 so-called capture modules and 1 so-called enhanced Ethernet switch. This is a concept of distributed testing system which fulfills all of the requirements of testing tools. We have realized this distributed system is the most efficient when it comes to testing, and in order to transport all the data that is captured, we use standard Ethernet. So you have one logging system in the end, let's say that's capable of 10 gigabit per second. You might need more than that, you might need less than that, and it's all using standard Ethernet for transporting the data, which is the reason why I'm showing this here today. You want these systems to be time synchronized. So in this animation as well, you can see the internal clocks of each of these modules. They have their own time whenever they start up. So they need time synchronization so that all the clocks are at the same level. For this, each of the devices needs to implement the time synchronization protocols, and also the central system that combines them all has to provide also master-slave functionalities. On GPTP, Automotive Profile, and so on, you can find a lot of other presentations, and Technica can also provide all the information that you need. And now, as is stated in the abstract of this presentation, which is one of the highlights, I want to go to the protocol that is currently being standardized by the ASAM. There's an international standard looking at the transport protocol that is used for CAN, LIN, FlexRay, RS-232, Automotive Ethernet, SerDes, analog or digital values that are captured from the communication inside the car, from ADAS, from infotainment, from telematics, from the body, from backbone, everywhere in the car, and funneled, or let's say summarized, into Automotive Ethernet. And then in that Automotive Ethernet packet, you need to have some way to identify what data is being transported there. So we have developed a protocol called Technically Enhanced Capture Module Protocol, also known as, or it's equivalent to a protocol of one OEM that's called PLP, Probe Logging Protocol. And this protocol is free and open for everybody to see, and now it's being currently standardized by ASAM. It provides the metadata that is needed to identify timestamps, counters, and so on. I will show this in a second in more slides. And open source tools that are worldwide used, like Wireshark, which is the most widely used tool in the world to test communication protocols, from the version 3.0 natively supported. Now, in the standard, obviously this will change a little bit, but obviously we will provide the Wireshark support for that as well. So how does it look like? You can see in this slide we have an Ethernet frame in green. So standard Ethernet frame has preamble, a startup frame, and then what's important, the destination MAC address, the source MAC address, an ether type and length, that in this case you can have something like a VLAN as well, that will tell you, tell the switch what to do with that. And then data, up to 1500 bytes, and then a CRC check. So what do we do here? Essentially, behind the VLAN and the initial ether type, we have a TCP header. By the way, the protocol name standardized via ASAM goes under the name PLP. Final name of the protocol might be completely different. This we will see. So this TCP header, what it does is it gives information on what data was captured in the car. You can see on the right side the car and its data, and then it's transported to the data logger, PC, sync storage device, however you want to call it, via Ethernet. In this green format means TCP header is wrapped around whatever data was captured. So what does the TCP header give us? It gives us information of the configuration of the devices at the moment of capture. So after the fact, you can always double check the configuration. It gives us the information of the logging. Did I capture FlexRay, CAN-FD, LIN, Ethernet, analog, and so on. It allows us features for injecting data. So in case you have XCP or DLT, you need to send something to your ECU. It gives information about cascading in case you have multiple capture modules that are cascaded to each other. Status information, so CAN errors, Ethernet counters, signal quality indicator, and so on. And it gives information about, it gives features of control where you want to modify something on the capture modules. So if you look at the header, we have, it's actually very, very simple. So you have here a normal header structure. So you have an ID that will tell you what capture module this data just came from. A counter, which is incredibly important, because if your storage device or logger loses packets, you can see it immediately on the trace wherever you are in the world doing the analysis. A version of the protocol, as I said, the existing version will change after the standardization, so you can see this every time. Configuration or status of whatever data is in the payload. Information of what type of payload do I have inside this Ethernet message, the Ethernet packet. A unique identifier for what port did this come from. Was it channel CAN A, CAN 1, 2, 3, 4, 5, CAN 29, which one? Was it a 100 base T1 port number 15, which port? This is information that's here. A timestamp that's big enough to be represented in UTC format. The length of the data that's coming in, you need this later for analysis. Some flags to give you information of what happened when it was being captured, and this is what gives you all the functionality that I mentioned before. How does it look like? This is a really quick presentation on Wireshark. an explanation here. You can see the Ethernet frame, the destination of the source MAC address. You can see the header in general with all the aspects that I mentioned to you, and then the payload, in this case just one CAN frame in one Ethernet message, but obviously there's also packetization, so you can put many CANs or many small Ethernet frames behind and put them all in one Ethernet packet. That's it about TCMP. If you have more questions of the standardization, you can ask us later on. Just one aspect I want to really remark on, the data logging, the source device, let's say the sync, whatever storage system you're using to capture your data, also is potentially going to be the single point of failure, just like it is in every communication system. The receiver, the problem number one when it comes to network issues is that the buffer of the receiver gets too full. So in this case, it's really important to remark you might want to have some buffering features on these kind of devices, which is obviously something we offer, in order to take care of spikes when it comes to the traffic. In this case, you could even use simple computers. For many use cases, when the average traffic is small enough, you could even save money and space, and you don't need a logger for many test benches if the average traffic is enough for the computer to capture. This might be really important on many of the test benches that I showed before, because it all becomes cheaper, faster to implement, and easier to use. So, in summary, I have given you some information of where Technica engineering comes from, what does it have to do with Automotive Ethernet, what are the quality requirements in general of data transport systems, what test considerations you have or we have find out are most important when it comes to testing Automotive Ethernet systems, what key aspects are relevant for any test tools when it comes to reliability, and some an overview of the state-of-the-art solution that we have for logging. Obviously there's many more things to talk about, best practices, but this one remarking the standardization on the ASAM protocol of TCMP. And I hope this was useful for you, and in order to keep in touch, please remark the contact data of our product distributor in Japan, the company Logic, our engineering partner in Japan, the company Toyo Corporation. We are also showing many of our videos in YouTube, so maybe the link does not work. You can just click go in YouTube Technica Engineering GmbH and you will find us. And if you have any questions, please don't hesitate also to send a message. And with this, I thank you very much for your attention.